6th International Physics Olympiad year 1972 IPHO. Problem number 4. A thin lens plane convex with the diameter 2 small r, the curvature radius big R, and the refractive index n0 is positioned so that on its left side is r, n1 equal 1, and on its right side there is a transparent medium with the refractive index n2 not equal to 1. The convex face of the lens is directed towards R. In the R at the distance s1 from the lens measured on the principal optic axis, there is a punctual source of monochromatic light. Question A. Demonstrate using Gauss approximation that between the position of the image given by the distance s2 from the lens and the position of the light source exists the relation f1 over s1 plus f2 over s2 equal 1, where f1 and f2 are the focal distances of the lens in R, respectively, in the medium with the refractive index n2. Observation. All the refractive indexes are absolute indexes. Question B. The lens is cut perpendicular on its plane face in two equal parts. These parts are moved away at a distance delta much less than r. Billet lens. On the symmetry axis of the system obtained is LED, a punctual source of light at the distance s1 greater than f1. On the right side of the lens there is a screen E at the distance d. The screen is parallel with the plane face of the lens. On this screen there are n interference fringes if on the right side of the lens is r. Determine n function of the wavelength. Solution for problem number 4. Part A. From the Fermat principle, it results that the time the light arrives from point P1 to point P2 is not dependent of the way. In Gauss approximation, P1 and P2 are conjugated points. Time t1 is the time the light roams the optical way. P1, V1, O, V2, P2. We have T1 equal P1m over nu1 plus P2m over nu2, where nu1 and nu2 are speed of lights in represented mediums. So we have P1m equals square root from P1o square plus mo square, which is approximately this expression, and the same thing for P2m, which is approximately this expression. This is because h equal om is much smaller than the P1o or P1o or P2o. So we have T1 equal approximately this expression, and the T2, the way from P1 through the optical axis, that will be P1 V1 over nu1 plus P2 V2 over nu2 plus V1 V2 over nu. So from the same approximation we have V1 V2 equal h square over 2 multiplied by 1 over r1 plus 1 over r2. And because we have T1 equal T2, we can equalize them and get such result. After subtracting P10 over nu1, P20 over nu2, and get rid of h squared over 2, we have this expression. Now because nu equals c over n0, nu1 equals c over n1, and nu2 equals c over n2, and also we have P10 equal S1 and P20 equal S2. Instead of equation number 3, we have equation number 4. If the point P1 is at infinite, S becomes the focal distance, and the same for P2. So we have 1 over F2 equal 1 over N2 multiplied by this expression, and the same thing for 1 over F1 equal 1 over N1 multiplied by the same expression. But these two expressions exactly equal to previous expressions in number 4. So we can combine number 4 and number 5 and find that 1 over F2 equal this one, and 1 over F1 equal this one. And the last thing is F1 over S1 equal this one, and F2 over S2 equal this one. Now we can just add them and get finally our result. F1 over S1 plus F2 over S2 equal 1. In our case, the lens is plane convex, like in this figure. It means that if we use expression from 5, we can get that for R2 equal infinity and R1 equal R, we will get these expressions, and that was a solution for the question A, problem number 4. Problem 4, question B. The lens is cut perpendicular on its plane face into equal parts. These parts are moved away at a distance delta, this one from O to O1 and from O to O2, such way that delta much less than R. Billet lens. On the symmetry axis of the system obtained is let a punctual source of light at the distance S1. S1 is greater than F1. On the right side of the lens there is a screen E at the distance D. The screen is parallel with the plane face of the lens. On this screen there are n interference fringes if on the right side of the lens is higher. Determine n function of the wavelength. Solution. In the case of a billet lens, S1 and S2 are real images of the object S, and they can be considered like the coherent light sources. Now let's count what happened. Suppose that distance from R to A equal to x. In that case we can estimate S prime A, this one S prime A, approximately equal D, this distance from lens to screen, minus P2, this one. And from this triangle SRA compared to triangle S prime Q, we have x over D minus P2 equal R over D. And finally, distance x from R to A equal D minus P2 multiplied by R over D. Now let's count what happened to distance S1Q. Suppose that S1Q, this one, equal to y. In that case, again compare triangles. We have y over P1 plus P2 equal delta, which is distance from 0 O2, O1 over P1. This is from these two triangles. And then from here we can find that y equal this expression, delta multiplied by 1 plus P2 over P1. And the last thing is distance QA, this one. That's equal to d minus P2. So now we have all parameters for prism S1R, R prime, S2. So that's a right prism with a known basis and no height. So from here we can find what is distance difference between S2R and S1R. Let's count it. So from the right triangle we can see that S1R square, that's equal to d minus P2 square, this one, plus x minus y square. So this distance minus this distance. And from other hand we have S2R square, this one, that's equal the same d minus P2 square, the height, plus x plus y square. Now we need to add x and y. And now let's count what is the difference between these two parts. In our assumption, we can say that this distance difference equal k multiplied by lambda, where k is maximum number of these interference fringes from one side, which is equal this difference. And when we take out d minus P2, we have this expression. And in this expression we have difference between square roots from 1 plus something small minus square root from other 1 plus something small. So we can use approximation. That will be this expression. And after calculations we have a simple expression, 2 multiplied by xy over d minus P2. And finally we can put x and y from initial expressions from the first and the second equations, and we have the k lambda equal 2 delta multiplied by small r over d and multiplied by 1 plus P2 over P1. And now we can remember what is focal distance f for our lens. That will be 1 over P1 plus 1 over P2 equal 1 over f. And we can put this P2 expression to this one, and finally we will get that k equal this expression. Remember that k is just half of our wavelength, and we didn't count zero interference. So it means that the total number n will be equal to k plus 1, which is this expression. That was a solution for second question of problem number 4.